So when you have a number like 123 million and then you are supposed to write it in the standard notation form, you are just writing it in the standard form, the ones we know from high school. And then the number here supposed to be between 0.1 and then 10. Right? So you can't write something like 12.3 times 10 to the power 9. You just have to move the decimal places starting from the very last number. So you get to a point where the number you are getting on your left hand side is between 0.1 and 10. So if you have an example like this, you're going to move 1, 2, 3, 4, 5, 6, 7, 8. You realize that 1.2 is between 0.1 and 10. And then how many decimal places did we move? 8. So times 10 to the power 8. We can also see the same in the Avogadro's number. It's very long, but then you have to write it in the standard form so that we can shorten it. And then we also look at significant figures. When you say significant figures, you are looking at how significant a value is or a number is. There are some rules you should take note of. The first one is the last digit on the right if there is a decimal point. So when I have a number like this, 2,300, and then there's a point here. So far as there is a dot here, then the number of significant figures would be you counting all the numbers till you get to the last number. So this will be 1, 2, 3, 4, because this is the last number. So this will have 4 significant figures. And a number like this also, even though from our normal mathematics, you might think this and this are the same, but when it comes to the significant figures, they are not the same. Because there is a decimal point here, you have to count everything to get to the last number. So 0, 1, 2, 3, 4. So 1, 2, 3, 4, 5. So 5 significant figures for this. And then the next rule is also the last non-zero digit of the number if there is no decimal point. So when there is no decimal point like this, you see with this one, we had a decimal point here. But then if there is no decimal point, when you write 2,300, then the number of significant figures will just be the non-zero numbers, right? So just 1, 2. However, if you have the zero in between two non-zero numbers, you are going to count that zero as part of the significant figures. So when you have 23,040, we are going to count as 1, 2, 3, 4. Then you end there because there is no decimal point. Now, what's the whole idea of the significant figures? When you report a mass or any figure or any measured amount of something, say you are reporting a mass as 8.3 grams, then the actual thing means that that mass 8.3 grams you are recording lies between 8.25 to 8.35 grams. And then you have to mute yourself too. Unless maybe you have a question. It lies between 8.25 and then 8.35. So now how do we get the idea that, or how do we get the range in which it lies between? So I'm just going to look at the unit number. So when I take 8.3, then I'm going to say, then the actual value lies between plus 0.5 of the unit number to minus 0.5 of the unit number. Okay, I think I've turned it. So minus 0.5 of the unit number 2 plus 0.5. So something like this, the 8.3, the unit is 0.1 because the decimal place is just 1. So 0.1, and then you find half of that 0.1, and that will give you 0.05. Then you can add that 0.05 to your 8.3, and that gives you the 8.35. So that becomes the highest value. And then the lowest value will be you subtracting the 0.05 from the 8.3, and then you will get your 8.25. So that means the actual number lies between 8.25 to 8.35. So in a case where you have 8.300, this has 4 significant figures because of the decimal point here. So you are going to find that unit number, and that unit number will be 0.001. 0.001. Then you find half of that 0.001, and that will give you 0.0005. Then you can add that to this, and then you subtract also to get the range in which the number falls within. Yes, so when it comes to multiplying two numbers together, mostly we associate the significant figures and those standard notations to measured quantities, not unlike unmeasured quantities such as, let's say, if there are like 16 oranges, That oranges can't be measured, like they're countable. Right? So there's nothing like 16.2 oranges or something. So when you are multiplying two measured quantities, so let's see, and then mostly the measured quantities are the ones that we don't get fixed values or we don't get whole numbers. So sometimes you can get something like 3.57 as a mass of something. When you are multiplying these numbers, the product that you are going to get supposed to be, first of all, you have to note the least significant figures between the two numbers you are multiplying. If it is three numbers, you have to look for the least significant figures between all the three numbers you are multiplying. And then your final answer, you leave it to that least significant figure. So when we take this, we have 3.57 multiplying 4.286. Now this 3.57 has three significant figures because of the decimal point. So we are going to count everything, 1, 2, 3. And this has 1, 2, 3, 4, four significant figures. Now when you multiply this is what you are going to get. But then to report this in the scientific way, we have to look for the between the two numbers, which of them had the least significant figure. That was this, and it was 3SF. So that means you are going to leave your final answer to three significant figures. So you count 1, 2, 3, right, and then 15.3. You look at the number after your last number. If it is 5 or more, you can add 1 to the previous one. But then when you look at this, when you count 1, 2, 3, the number after the 3 is 0, which is lesser than 5. So our answer will just be 15.3. The same applies. So for multiplication and division, they'll go by the same rule. When I have this multiplied by this divided by this, I have to evaluate everything. Then after, I'll come and look for the one in the least significant figure. So this 5.2, it has two significant figures. Then you can count 1, 2. So 1, 2. And then look at the number after the 1, which is 8. It's more than 5. So you can add 1 to the 1 here, making it 2. And then your answer will just be 320. And note 320 is two significant figures because there is no decimal point here. When it comes to division, it goes with the same rule as the multiplication. Right? So anytime we are dividing two numbers, in this case we had three numbers, two were multiplying and one was divided. So this one had two significant figures. This one had 4 and this one had 3. So after evaluating everything, this is what you will get. So you're going to leave your answer to two significant places. Right? So when I count this 1, 2, so this is how I'm supposed to end. But then 8 is greater than 5, so we add 1 to the 1, making it 2. So that will give you 320. And I was saying that to take
Yes,
so for
please.
division and multiplication, you look for the least significant figure, and then you leave your answer to that last permissible significant figure of the sum or differences. So when you have two numbers, this the position of the last significant figure. So with this one, because there is no decimal point, this has three significant figures. So the last significant figure, this one also has 3, which is the 6. It's farthest on the left. And when you compare that one, the one that comes early, third one here, and then this one is the third one here. So that means you have to leave your answer to three significant figures. So after getting this, to convert this to three significant figures, before because there is a decimal point here, this will have like 6 significant figures. So you have to count 1, 2, 3, and then look for the number after the 2. This is 7, which is greater than the 2. So you add 1 to it, making it 3, and that will give you this. And this has the three significant figures. Now, with this part, we are talking about dimensionally homogeneous and consistent. The consistency here is that when I take this equation, u equals u naught plus gt, the u here has a velocity dimension, which is true. This also has a velocity of dimension. When I multiply these two, it gets a velocity of a dimension as a velocity, which is also that makes everything here dimensionally homogeneous. But the consistency comes in because of the units. Now, if I had this as meter per second, and this was in feet per second, and this also in meter per second, it's still dimensionally homogeneous, but then they are not consistent. The units are not consistent. So in a case like that, I can't just add them. So before you can add two or more quantities, you should make sure that they are dimensionally homogeneous and consistent. If they are not consistent, what you have to do is to do unit conversion. But then if they are not dimensionally homogeneous, then it means your equation is wrong. And then yesterday too, we even spoke about dimensionless quantity. Now, with the dimensionless quantity, when we take any exponent, such as x squared here, you should make sure that the power here is always a whole number or a dimensionless quantity. Not only x squared, but then all exponent, transcendental functions, and argument of transcendental functions. So the transcendental functions examples are the logarithmic functions, the exponential function, the sine, cos, and all that. When you have such, when you are dealing with such expressions, you should make sure that, or you should know that the actual number itself should be a dimensionless quantity or should be a pure number. It shouldn't have a unit. So even if it has a unit, let me see, there's a problem somewhere. For instance, when I have something like this, you writing 10 to the power 2 feet here is meaningless. Supposed to be 10 to something like that. Yes. So when you have an expression, say exponential y times t, right? Y times t, where the dimension of t is in seconds, then you should know that the dimension of y will be per time, which is per second. So that when the two multiply together, they cancel out, leaving it as a dimensionless quantity. So the same applies to the exponential functions and the logarithmic functions. Supposing you have an expression, let's say log multiplying k times f, and then we know the dimension of f as, let's say, joules, then we should know that the dimension of k will be inverse of joules. Yes. So one example of a dimensionless quantity is what we call the Reynolds number. It's also it's a useful quantity when it comes to fluid phenomenon, but then it's a dimensionless quantity. And the formula is d here is the pipe diameter, the v here is velocity, r here is density, and r here is viscosity. Now, when you look at all these, after manipulating everything, which could be in centimeters, when our velocity is in centimeter per second, our density here is in gram per centimeter cube. Our viscosity, you said viscosity, is gram per centimeter second. But since it's a denominator, it goes up, right? So gram per centimeter second. Everything cancels as less quantity, right? But see, do they have any significant use? An example is the Reynolds number here. So when we say a process is any operation or series of operations by which a particular objective is accomplished. And then we looked at distillation columns and all that, and I was like, those equipment there are process units. They are the ones in which the actual processing takes place. Right? But here we are going to look at processes and the process variables. So when you talk about the variables, you are looking at what actually goes in. If you are talking about the distillation, then what is the pressure? What is the temperature? Right. So that's what you call the process variables. And we talked about process unit too. The equipment where the operations takes place. Example, mixer, which is used for blending. So if this becomes our process unit, we feed in our input and then there's an output. Now let's look at mass and volume. Um, Density, we spoke about it yesterday. So, and we also have a new term here, specific volume. I'm pretty sure this new to most of you here. Specific volume. When you say something is specific in chemical engineering, we mean it's per mass or per moles. So when you say specific volume, it's a volume, yes, but then it's volume per something. Specific gravity. So you have something like specific gravity. So it's like gravity per something or density per something. So anytime you see specific, just know that it's per something, either per mass or per moles. So the unit for specific volume is meter cube per kilogram. You can also have it as meter cube per mole and it's still specific volume. So you can even realize that the density here is even specific. Why? Because it's mass per something per volume. Right? I think as time goes on, we'll get much insight about these specific things. And then this part also talks about density of pure solids and liquids and how they are impacted by pressure and then temperature. Mind you, we are looking at process variables, so temperature and pressure is what we'll be looking at. When you
Francis.
take density of substance, yes, the whole idea of the specific is you are trying to make it in a way that it does not change. How am I saying that? So let's say if I take the density, for instance, when I take density of water, right? When I take 1 cup of water and a barrel of water, the density will still be the same. Please, are you okay? That's why you are trying to make it specific. If you are doing it in terms of mass, fine. If you are doing it in terms of mole, fine.
Okay, so
Yes,
what I want to add to that is, so uh, it's just a choice. Remember, like we know the molar mass of everything. So it means that if we knew it in meter cube per kilogram, then we could have converted it to meter cube per mole too, right? We are
yes.
converting that 1 kg to moles.
Mm.
So even you see, you guys say density, and it's not really so. Like concentration is molar density. Then the one you call density is mass density. So they are all densities. Just that one is moles, one is per what mass. The same way people also call density mass concentration, and they call the normal concentration molar concentration. So because we know the molar mass, you can always convert mass to moles. Anything which is per kg, it means that there's a version where which can be per mole.
The density is being varied or both temperature and pressure affect the density. So for you can realize that for ammonia like this, the density changes that much as the temperature also changes because the density, and mind you, the density that we know here as mass per unit volume, when it comes to gas, it's not like that. It really depends on temperature and pressure. So they really have impact on the density when it comes to gases. So we can use this one to, I mean, have a clear picture of it. For ammonia, realize that the density actually changes that much when we increase the temperature as compared to water here. We can also use the density as a conversion factor. Like what Doc was saying, if you have something per kilogram, you can try and convert it to per meter cube. And then you can use the density also. So for example, when you have the density of a carbon tetrachloride to be 1.595 gram per centimeter cube, and then you have the mass, you need to find the mass. If you have the volume, then we can use that to find the corresponding mass. Did I do something here? So first of all, density is mass over volume. I think we did similar thing yesterday. So when we want to find the mass then becomes density times volume. And then if you have our density to be 1.595 gram per centimeter cube, and then we have our volume, we can just multiply them. In this case, the density here is acting as a conversion factor. Why? Because if you have our volume here, now I want to convert it into grams. So like 1 centimeter cube is equivalent to 1.595 grams. And that's what we are calling as a conversion factor. So it means when you take 1 centimeter cube of carbon tetrachloride, it has 1.595 grams of it present. And that becomes a conversion factor. And then you can use it to convert from volume to mass. So you can try out this question too. What would be the volume of 90 gram of alcohol if the density is 0.804 gram per centimeter cube? So you try out that. This is what you will get as your final answer. Let's talk about specific gravity. It's the ratio of the density of the substance to the density of a reference substance. So but mostly we use water as our reference substances. So when we talk about specific gravity of any substance, it's just the density of that substance to the density of water. When you divide both, what you get becomes the specific gravity of that material. But for gases, we use air, and then for liquids, we use water as a reference. If it is a gas, you use air as the reference. And then if it is water, if it is a liquid, you use water as a reference. And the density of water, this is the maximum density of water. It occurs at 4 degrees Celsius and it's 1 gram per centimeter cube. When you convert it into kilogram per meter cube, it's 1000 kilogram per meter cube. And when you convert this to pounds per feet cube, you get 62.43. So depending on what you are using. So if let's say you need to find a specific gravity of any liquid, but then the density of the liquid is given in pounds per feet cube. Then you can't use this density of water. You need to use this density of water to give you the specific gravity. Density is the mass per unit volume of a substance. So it's like when you take any substance, any volume of a substance, what quantity of mass does it possess? That gives you the density. But when you talk about specific gravity, we are trying to compare two things, like the density of something in reference to another material. Specific gravity of the density of a substance to the density of to a reference material. That reference material could be anything, but the ones which are commonly used, it's water. Use water as a reference material. For gases, we use, if we are trying to find a specific gravity, this is the formula we use. Density of the substance divided by the density of the reference material. But water for liquid. So density of the substance over density of water. Now, the unit should be the same. The density of water you are going to use is 1000 cube. So if you are given the specific gravity of a substance, you just have to multiply by the reference density in any unit to get the density of the substance in the same unit. What this is trying to say is that we know from here that specific gravity is the density of the substance divided by the density of the reference material. So now when I know the specific gravity of a material, let's say it is 0.7, when I want to get the density of that material, I just have to multiply by the density of water, right? And the density of water, mostly is a constant, it's fixed. Either 1 gram per centimeter cube, 1000 kilogram per meter cube, or 62.4 pounds per feet cube. So if I need to find the density of that material and I know its specific gravity, depending on the unit I want to find the density in, then I can choose any of these. If I need to find the density in gram per centimeter cube, then I just have to multiply the specific gravity by 1 and I'll get 0.7 gram per centimeter cube, and that will be the density of that substance. If I want the density in kilogram per meter cube, then I need to multiply 1000 by the specific gravity here to get the density in kilogram per meter cube. The same applies to when I want to find the density in pounds per feet cube. That's what this is trying to say. So if the specific gravity of a liquid is 2, then its density becomes 2 times 1000, and that will give you kilogram per meter cube. Or it can just be 2 gram per centimeter cube. Consider the density of water is 1 gram per centimeter cube. And then if you want it in pound mass per feet cube, then you just have to multiply it by the 62.43 here. So we can try out this question. Calculate the density of mercury in pound mass per feet cube from a tabulated specific gravity and calculate the volume in feet cube occupied by 250 kilogram of mercury. Okay, so we need a reference book to get the specific gravity. But let's say we've gotten the specific gravity. I don't know what they give. Okay, so the specific gravity was 13.546. Now, I've already established the fact that for liquids, we compare it to the density of water. So when I want to find the density of that mercury, I need to multiply this 13.546 by density of water. But then since I need pound mass per feet cube, I have to go for the density of water that had the unit of pound mass per feet cube, and that was 62.43. So I multiply these two and I get 845. 845.7 pound mass per feet cube, and that will give the density of mercury. If you need to find the volume here, now because they gave the mass in kilogram, you can't use this pound mass per feet cube alone. You need to do unit conversion again so that you can get it in kilogram per meter cube, and then you can use that to find your volume. But then if you want your volume in feet cube, then you should know how to do your conversion. We have this in pound mass per feet cube. So if I need to find the volume, that means I have to get rid of this pound mass and then get only the feet cube.
Are we using 20 degrees Celsius because it's liquid at that temperature?
No. The reference book, if you have gone to the reference book, they give the specific gravity based on temperature and pressure. I think I didn't talk about that one. You see, to be precise, when referring to specific gravity, The data should be accompanied by both the temperature of the substance of interest and the temperature at which the reference density is measured. So when you write, where is it? I'm sure from the reference book, they gave the data at this particular temperature. If the temperature had changed, so let's say if the temperature was around 40, the specific gravity would have changed slightly. So from this chart, you realize that for water at this 20 degrees Celsius and at let's say 40, the density is still the same. It doesn't really change. But then for the gas, it was changing. So it means that when the temperature changes, there's a chance that the density might also change. So you need to give the temperature at which you took the value of that density from. The density is not fixed, as in density of ammonia is always this. No, at this particular temperature, this is the density. So the same applies to this one too. So at that 20 degrees Celsius, this was the specific gravity, and that's what you are working with. If you had changed the temperature here, the specific gravity would have changed slightly.
Okay,
Please,
and
your question
Francis,
answered.
so how do we know what temperature to use?
That's why we have a reference book there. So the reference book has a table with values inside. At the top, every table has a reference. So if you want to work at this particular temperature, then you have to look for a reference book that has that particular temperature and the densities beneath it.
Okay, and Francis, can I add something?
Okay.
Yeah, so you realize that maybe you are doing a particular experiment or you're working with a particular system, and then you have mercury, and the temperature that your mercury is at is maybe 20 or maybe 15, and you want to now use it to determine other properties. So when you go for your references, you look for the properties of the substance you have at those conditions so that you can use it for your calculations and for your analysis. So for the particular kind of temperature to use, if it's supposed to be a real life and a practical thing, you would work based on the properties of the material you have. So maybe if we had mercury at 15 degrees Celsius instead, would have looked for the specific gravity of mercury at that condition. But then this is just an example that we are using. And from the reference material we are looking at the temperature of mercury at 20, sorry, the specific gravity of mercury at 20 degrees Celsius, just for the sake of, just for an example purpose.
Yes, so that's it. So when you do that, you have your density to be pound 845.7 pound mass per feet cube. If you need to find the mass, then you know what you should do to get. So if you need to find the volume in feet cube, then you should get rid of this pound mass. Right? But then the mass they give you here is kilogram. So you need to convert that into pound mass so that it can cancel what's here. So you first convert 1 pound mass is 0.454 kilogram. I think yesterday in the slides I sent, I converted kilogram rather into pound mass. So 1 kilogram was around 2.205 pound mass. So when you do that, your kilogram can cancel out, and then you get your mass in pound mass. Then you can multiply by the inverse of your density here. So that your pound mass also cancel out. Then you get your volume in feet cube. So let's look at the fundamentals of material balance. Most processes involve the movement of material from one point to another, sometimes between process units. Right? So like what we saw here. Yes. So we see there is always something entering and then something coming out. So that's what we are looking at. Most processes involve the movement of materials from one point to another. So the whole idea of the material balance is to account for what's actually going in and what's actually coming out. Right? The rate at which a material is transported to a process line is the flow rate of that material. So when we say a flow rate, we're just looking at what rate is the material being transported. And when you say rate, we are talking about time. So anytime you hear flow rate, just know it's something being transported per unit time. For here, when we talk about mass flow rates, then we are trying to see that what mass is being transported through a process line per unit time. So the unit time becomes kilogram per minute. Sorry, kilogram per time. So if your time is in seconds, kilogram per second. If it is in hours, kilogram per hour. If it is in day, kilogram per day. Right? So mass flow rate always have a unit of mass per time. And when you want to look at volumetric fluid, it will also be volume per time. The fluids, there we have a lot of them. We can also talk about molar fluid. That means that will be moles per time. So just have this in mind. Anytime you talk about fluid, you are talking about something per time. So suppose a fluid flows in a cylindrical pipe shown below. Right? So let's say we have as our pipe, and then there's a fluid flowing through. How much mass of it does it flow per every second or per every minute? That's what you call a mass fluid. And then when we talk about the volume too, how every minute, how much volume does it flow? That's also what you are looking at the volumetric fluid. So our mass fluid is noted as M with some dots on it, V with some dots on it. You can choose to use any symbol, but then when you use M alone, mostly for mass, just kilogram. But then when you put just mass. Now density is mass over volume, and then it could also be written as mass fluid over volumetric fluid. But note, if your mass is in mass fluid and your volume is not in volumetric fluid, then you can't divide them and get to density. The same applies to when you have your volume in volumetric fluid and then your mass is not in the mass fluid. You can't divide them and get to density. Make sure that your units are consistent. The mass flow rate of N-hexane, which is normal hexane, with a density of 0.659 gram per centimeter cube in a pipe is 6.59 gram per second. What is the volumetric flow rate of the hexane? So you just have to go back to this. We know density equals mass flow rate over volumetric flow rate. So when I need volumetric flow rate, I have to divide the mass flow rate by the density, and that will give me the volumetric flow rate. The volumetric flow rate of carbon tetrachloride with a density of 1.595 gram per centimeter cube in a pipe is 100 centimeter cube per minute. What is the mass flow rate of the carbon tetrachloride? So the same thing, just change of subject. Now in measuring the flow rate, you use instrument to measure them. You can't just be sitting down looking at it and then try to figure out how much mass does it flow per every second. So there are units or devices, there are devices used to measure the flow rate. And a typical example is the rotameter and also the orifice meter. So these are used for measuring flow rates. Orifice meter, rotameter. The other equipment also. Let's look at chemical composition. You guys did this in inorganic chemistry, so I wouldn't talk much about it. We're going to talk about atomic weight, molecular weight, and then gram mole. I think I have to talk about this a little. When you talk about the gram mole, it's just the same as a mole. So anytime you see gram mole, just know the same as moles. Right? Yes, it doesn't change anything. The fact that it's gram doesn't mean it's different from moles. What they are trying to say is that we know that to find moles, it's grams, or let's say it's mass over molar mass. So that mole we are finding is a gram mole. Just like what Doc said, like you have density and you have mass density. But then the density that we know as kilogram per meter cube, in some places you call it as mass density. It doesn't change, it's still the same thing. The same thing applies here. When you see kilogram moles, just know that it's kilomoles. So kilogram moles is the same as kilomoles. So anytime you see this, you should take note. They are the same. And you guys did organic chemistry, so you know much about this molecular weight. And the unit is gram per mole, kilogram per kilomole, pound mass per mole. But then with the molecular weight, irrespective of the unit, the actual value doesn't change. It's still the same thing. So when you take carbon monoxide like this, the molecular weight is 28. The reason why they didn't add any unit here is because irrespective or regardless of the unit you are going to use, you are still going to end up getting the same thing. So if the molar mass of carbon monoxide is 28, in terms of gram per mole, it's still 28 gram per mole. In terms of pound moles, pound gram per pound moles, it's still the same thing. It doesn't change. So like this, what's the molecular weight? Yes, for oxygen. So most of the times you can see molecular weight and then there is no unit. It doesn't mean it's a dimensionless quantity. But the idea is that the unit doesn't really have effect on the magnitude of the molecular weight. So molecular weight of oxygen is fixed, 16 gram per mole. Even if I convert it into pound mass per pound mole, it will still be 16. So 34 kilogram of ammonia is equivalent to We can use the molecular weight also as a conversion factor, just like how we use the density. Because we are saying that molecular weight has a unit of gram per mole. So it means that when I take 1 gram of, let's say, carbon dioxide, what's the number of moles present in that 1 gram? And that makes it a conversion factor. Just like when I say 1 kilogram is 2.2 pounds, the same thing. 1 gram of carbon monoxide will contain how many grams of moles? Or when you say, let's say, carbon dioxide, the molar mass is 44 grams per mole, which means that 44 grams of carbon dioxide will give you just 1 mole of carbon dioxide present. Or let's say when I take 1 mole of carbon dioxide, there's 44 grams. And of course, you can't measure moles. So we measure the mass and then we get the moles present. So when you have 34 kilogram of ammonia, what will be the number of moles present? We know the molecular weight here is 17. The reason why there is no unit is that the unit doesn't change. The fact, or the moment you realize that your mass here is in kilogram, then you just have to attach kilogram per kilomole to your molecular weight here. So now your molecular weight here becomes 17 kilogram per kilomole. Please, if let's say in a question they give you the molecular weight to, let's say, 17 pound mass per pound mole, and then your mass is in kilogram, you don't have to do unit conversion and convert the pound mass per pound mole to kilogram per kilogram before you start solving. When you do that, you're just wasting your time because you end up getting that 17 again. So moles is mass over molecular weight. So 34 kilogram of ammonia multiplying, so this is where the unit conversion comes in. 17 kilogram of ammonia will contain 1 kilomole. So what will 34 kilogram will contain? Right. So we use this as a conversion factor. Because there is kilogram here, you should make sure that the kilogram will be at the bottom here so that it can cancel out. So I was saying that molecular weight, most at times you don't add a unit to it because regardless of the unit being added to it, the magnitude doesn't change. It's still the same thing. Even though we know molecular weight has a unit of mass per moles, and the mass can be in kilogram, and then our moles is also in moles. Fine. Now, when you measure our mass in pound mass, and then our molecular weight now becomes pound mass per pound mole, the values is still the same. So for instance, when I take let's say carbon dioxide, it has a molecular weight of 44 gram per mole. If I convert that to pound mass per pound mole, it's still 44. We have pound mass, which is mass for other people, and then pound mole is also moles for other people. It's just the system in which you are doing your measurements. Yesterday I spoke about the American engineering system and then the British system also. So the value doesn't change. So I was saying that supposing here they give us the molar mass to be 17 pound mass per pound mole, we should know that this 17 pound mass per pound mole is the same as 17 kilogram per kilomole. So we are going to use the kilogram per kilomole rather because our mass here is in kilogram. If our mass here were to be in pound mass, then we are just going to say our molar mass is 17 pound mass per pound mole, and then we can do our calculation. So from here, you can use the formula. Mole is mass over molecular weight. So when you want to find your moles, you just have to divide the mass by the molecular weight, and then you are good to go. If you want to use your conversion factor approach, then you are saying that there is 34 kilogram of ammonia, but then you want to find moles. The conversion factor is 17 kilogram of ammonia contains 1 kilomole of ammonia. So what will 34 kilogram of ammonia contain? So when you do the conversion factor, because your kilogram is here, you should make sure that your next kilogram will be a denominator so that they can cancel out here. And then to be 34 times 1 divided by 17 or kilomole of ammonia, and then you get this. So now when you have pound moles of ammonia is equivalent to, now because this is now in pound moles, then our molar mass here will now be pound mass per pound mole. We are not going to use kilogram per kilomole. even though the value will still be the same. So 4 pound moles of ammonia, we want to convert that into pound mass, IBM. So you're going to use the conversion factor. You can still use the formula here. If you want mass, you just have to multiply your moles by your molecular weight. By the conversion factor, 17 pound mass of ammonia contains 1 pound mole of ammonia. Right? So what do 4 pound moles of ammonia contain? Because this is a numerator here, kind of, we have to make sure that our moles here becomes a denominator. So this and this cancel out. Now you can have 4 times 17, and that will give us 68 pound mass of ammonia. Just make sure that your units are consistent. So you can try this one out. How many moles are contained in 100 grams of carbon dioxide? Then you can find the moles. It flows through a pipe at a rate of 100 kilograms per hour. The molar flow rate of the carbon dioxide becomes, from here, we know that mole molecular weight. Now, when you're talking about mass flow rate, and we still want to use this formula, then you should take here now becomes molar flow rate. Please, are we okay? But then if you want to deal with fluids, then our mass supposed to be our mass fluid, our volume supposed to be our volume fluid. The same thing applies here. Molar fluid will be equal to mass. So like I was saying, density is equal to mass over volume. Now when you want to use the fluid, it will be mass fluid divided by molar fluid. So the same thing applies here. Our moles is mass over molar mass. When we want to talk about molar fluid, it will just be moles fluid should be equal to mass fluid divided by molecular weight. Yes, so our question is, if carbon dioxide flows through a pipeline at a rate of 100 kilogram per hour, then the molar fluid is, so you just have to do change of subject, or you can still use your molar mass as a conversion factor. We want to convert 100 kilogram per hour of carbon dioxide to kilomole per hour of carbon dioxide. Now, so the conversion factor is 1 kilomole of carbon dioxide contains 44 kilogram of carbon dioxide. So this and this cancel out, and then you are left with 100 over 44, and that will give you kilomole of carbon dioxide per hour. It's still the same as using the formula like that. But I just have to make sure that your units are consistent. If this was in gram per hour, then your molar mass is supposed to be gram per mole. So here your answer would have been moles of carbon dioxide per hour, not kilomoles. So I was saying that the carbon dioxide is flowing through the pipeline at a rate of 100 kilogram per hour. Now when you want to find the molar fluid, because here the mass is in kilogram, then your molecular weight is supposed to be kilogram per kilomole, right? Supposed to be in kilogram per kilomole, so that your kilogram and your kilogram can cancel out, and then your answer will be kilomole of carbon dioxide per hour. But in a case where your mass fluid was 100 gram per hour, then your molecular weight here will now be gram per mole. And if your molecular weight is in gram per mole, then your final answer would have been mole per hour, not kilomole. If the output stream from a chemical reactor contains carbon dioxide flowing at a rate of 850 pound moles per minute, the corresponding mass flow rate is. So a similar question like that. Now we have our mole flow rate to be in pound mole per minute. Our molecular weight here should have a unit of pound mass per pound mole, right? So here we are not going to use kilogram per kilomole, even though that 44 will still be there. Make sure that your unit is correct. Your unit will be supposed to be in pound mass per pound mole. And then when you multiply them, you get your final answer as this. So just make sure that your units are consistent. Now, we also look at mass and then mole fraction. I think this will be the last thing we talk about. Yesterday, we mentioned mass fraction and mole fraction as dimensionless quantity. When you have a mixture of liquids, or let's say a mixture of gases, let's say I have a container and then the container contains more than one species. So the container contains something like component A, component B, and component C. When you talk about mass fractions, you are just looking at when it comes to the weight wise, what is the amount or how much does each of the components contribute to the entire mixture. And that's what you are calling as the mass fraction. So to find the mass fraction of a certain component, let's say you're looking at component A, in terms of weight, how much does it contribute? It will be the mass or the weight, or no, sorry, it will be the mass of component A present in the mixture divided by the total mass. But you just have to make sure that your units are still consistent. So when you divide that, that's what you get as your mass fraction of A. If you are using mole fraction, then it's supposed to be the moles of that component A divided by the total moles. But take note, I used XA here as mass fraction notation, and then YA here as mole fraction. So when I want to find the mole fraction of A, then it's supposed to be the moles of A present in the mixture divided by the total moles. When you do that, because it's a fraction, part of a whole, when you do that, your answer will always be a decimal. Sorry, your answer will always be less than 1. You can't get mass fraction to be greater than 1. It can't even be 1. So you take note of that. But then we can multiply it by 100 or 100% to get it as a mass percent or a mole percent. So when you multiply 100 by your mole fraction, you get mole percent. When you multiply your 100 by your mass fraction, you get mass percent. So let's try this example here. A solution contains 15% A by mass. So 15% A by mass, it means the mass fraction of A is 0.15 because it's 15 over 100. So meaning there is 15 grams present in 100 gram of the mixture. We said mass fraction is mass of A divided by the total mass. So when we say a solution contains 15% A by mass, so it means that when we are taking 100 grams of the solution, 15 grams is A. So now your mass fraction will become 0.15, or we said mass percent is 100 times your mass fraction. So now if you want your actual mass fraction, you just have to divide by 100. Said a solution contains 15% A by mass and 20 more percent B. So we are just looking at the first part of the question. 15% A by mass. So what we've been given here is mass percent. And then we said mass percent is equal to 100 times your mass fraction. So if you want to find your mass fraction, you just have to divide your mass percent by 100. Then you get your mass fraction as 0.15. But then I was trying to explain that what that 15% means. It means that when you take 100 grams of the mixture, the whole idea of this mass fraction and mole fraction is that we have a mixture, but the mixture consists of component A, B, and then other components. Sometimes it could be just a binary mixture, just A and B. So like we are putting A and B together, everything becomes the mixture we are talking about here. When you take 100 grams of that mixture, there is 15 grams of A present. That is the meaning of this 15% here. So our mass fraction here, if you want your mass fraction, just know that 100 times your mass fraction will give you your mass percent. And then you've been given mass percent here. So you just have to divide by 100 to get your mass fraction. Here too, you were given mole percent. So when you want to find the mole fraction of B, you just have to divide by 100, right? Because 100 times your mole fraction will give you mole percent. And the first question is, calculate the mass of A in 175 kilogram of the solution. Now, we said that there is a mixture, but that mixture, we don't know the actual mass it contains, but then we've been given a mass percent of just one component, and the component is 15% of it. So it means that when I take 100 kilograms, because here they are giving us 175 kilograms, I'll just talk about kilograms. I will say when I have 100 kilograms of the mixture, 15 kilogram is made up of A. I'll just say that When I have 100 kilogram of the mixture, 15 kilogram is occupied by A, or 15 kilogram is made up of A. So now in a case where I have 175 kilogram, how much of it to be occupied by A? Just like relation proportion. Please I write something like 100, so let's see, 100 kilograms is equivalent to 50 kilogram of A. Then 175 kilogram equivalent to what? So you can use that sense. We know that mass fraction is mass of A divided by the total mass, right? Now we know to be 0.15. 0.15 is equal to mass of A over my total mass. So my total mass here will now be 175 kilogram. And I'll just multiply, get the mass of A. So the mass of A will now be 0. Mass of A. So the next question is calculate the mass flow rate of A in a stream of solution flowing at a rate of 53 pound mass per hour. So now this one is in terms of flow rate. We are still looking at the A, right? So you can use the same thing here. So we are still going to use the same approach. Mass fraction is equal to mass fraction is equal to mass of A over the total mass of the solution. You multiply them and then you get your mass of A. But here you're looking at flow rate, it will still be the same. So mass fraction is equal to mass flow rate of A divided by the total mass flow rate. And from here, the total mass flow rate is 53 pound mass per hour. You just have to multiply your 0.5 by the 53 pound per hour. And then you get your 8 pound mass of A per hour. Now this one is calculate the molar flow rate of B in a stream flowing at a rate of 1000 moles per minute. So this for the B part. The mole fraction is 0.2. So we apply the same thing. Mole fraction is equal to moles of A divided by the total moles. But here if you are looking at mole flow rate, then to be mole flow rate of B divided by the total mole flow rate. And then, but let me add one more thing. Talking about the mass fraction, I said that we are looking at a mixture which consists of multiple components, so A, B, C. Now, when you add all the mass fraction of each of them, the answer you should get should be 1. When you sum all their mass percent, you should get 100% because the mixture is made up of all these components. So when you add all of them, their mass fraction, you should get the total mass fraction, which is 1. When you add all of them, their mass percent, you should get the total mass percent, which is 100. Please, are we okay? So with this question, if the solution contains only A and B and the mass percent of A was 15%, the mass percent of B will be 85%. And then if the moles percent of B was 20%, then it means the moles percent of A will be 80%. Take note of this. Mass percent is not equal to mole percent. So in the same mixture, it can have 20% by mass of A and 80% by mass of B, but then their mole percent will differ. You can try out this too. You can try out this. Now, I think this will be the final thing we talk about. Basis of a calculation. Now, in chemical engineering, when you talk about mass fraction, like I said the mass of A over the total mass. Sometimes you might not even know the total mass, just like how this question was. A solution contains 50% of A by mass. Realize that we are just making changes to the total mass. We are like calculate the total mass of A present if the total mass of the solution was 175. And then here we said if the total mass flow rate is 53. So in actual sense, you don't really know the total mass of the solution, but then, or this is the total mass of the mixer. But then we know the mass fraction or what percentage does a component of them possess as compared to the total. That's what the idea of basis comes in. So the basis means that we can actually decide to choose any mass that we want for the total mass because we don't know it. So when you are solving you are performing your calculation, you can choose any mass of the total solution that you want, and that's what you call as the basis. So for this question, you could have said that the basis here was 175 kilogram. That becomes our basis. That we are saying that the total mass of the solution is 175. So what would be the total mass of A present? And then that's 26 kilogram of A. If you write from the mass fraction or the mass percent, you can use that to set a basis. I can say that because the solution contains 50% of A, then I'm assuming that the total mass of the solution was 100 grams. So 15 grams was A. Just like when you write exams, sometimes you can write exams and then it's being marked out of 20, but then you can convert it into 100%. That's the same thing. So when you get like 80% in an exams, the basis is that the total marks is 100 and you've gotten 80% of it. Right? When you bring the basis down to 20 and then the lecturer decides to mark it over 20, someone who had 80% now will get around 16. Why? Because now we are saying that the total marks is 20. If the total marks is 20, what will be the marks that you will get? So just like you are choosing a basis. So with this one, you don't know the total mass. We don't know. But then we said the question is saying that the mixture contains 15% of A. Right. So I can decide to choose a basis of, let's say, 100 grams, and I will say that the mixture contains, or the total mass of the mixture is 100 grams. So 15 grams is for A. Someone can also see that the total mass of the total mass of the mixture is 1 gram. So 0.15 gram is for A. And the person is still correct. So that is the whole idea of you assuming a basis for your calculation. You don't know the total mass of the mixture. So you can decide. You can choose 100 kilogram or 100 pound mass. You can choose 1 gram. But you should take note that the basis you are choosing wouldn't change your calculation, but then it can make your calculation tedious. Because if someone chooses 1 gram as a basis, that means you're actually going to work in decimals, like 0.15, 0.2, which might make your calculation complex. So with this question like this, if I choose my basis to be 100 grams, then it means my mass of A is 15 grams. But then someone who would choose the basis to be 1 gram will have a mass of 0.15 gram. And then if you are supposed to use it to solve other questions, I feel like this might be a little bit complicated, like working with decimals, 0.15, 0.12, and all that. And then the B. So the A is saying that assuming as a basis of calculation for a mass of the mixture. And then the B, using the known mass fraction to calculate the mass of each component in the basis quantity and converting these masses to moles. Okay, sorry. So the whole idea of this particular slide is just talking about how to convert mass fractions to mole fraction. It's the same mixture. We know mass is different from moles, but then we can convert one to the other. Right? Yes, and then in doing that, you first have to set your basis if you don't know the total mass of the mixture. When you set your basis, then you can find the mass fraction of each of them, or let's say the mass of each of them. Then you can use that to calculate for your moles of each of them and then find your mole fraction. You've been given mass fraction. You need to get mole fraction. You first have to get the masses of each. Convert the masses of each into
Good, how are you? The
moles.
last. Hello, guys. So another way you can see a basis is this. So assuming someone says, how do you send money? You cannot just start talking. You might have to say, let's say I have 1 million. Then I will put this amount in this. You get my point. So you are using the 1 million to help you kind of crystallize what you want to do. Because otherwise, so you have an idea that you want to take some to this, want to take some to this. Maybe you want to use 20% for food. But if you don't use some actual money, it looks like you'll be talking in a hypotheticals. Is that okay? So the basis is choosing some amount that you want to base your calculations on if you are not given.
Yes. So That's the whole idea of the basis of your calculation. And then regardless of the basis that you are going to choose, you will end up getting the same fraction into masses. Convert your masses into moles because you know how to convert mass to moles. Moles is mass over molar mass. So you do that and then you convert. And then when you have the moles of each component of A, to just be the moles of A divided by the total moles. Same way when you have mole fraction, you want to convert them into mass fraction. You and then you can calculate the moles for each of them. Mass is equal to moles times molar mass now. And then you can sum all your masses and then you can divide them to get the mass fraction for each. So there's a question. So this all come together to form the mixture. And then oxygen has 16% of the composition. Carbon monoxide has 4%, has 17%, and nitrogen gas has 62. This into mole fraction. Sum everything up to see if it's up to 100. And then so the total, when you sum all the mass percent, you should get 100%. Now we want to convert this into molar composition. From the question, we don't know our total mass, and that's how always the question is. That's how always the question comes in. We don't know the total mass. That's why you have to set your basis. So I can decide to set a basis of 100. So from this, I'm setting a basis of 100 gram of the mixture. So if I'm setting a basis of 100 gram, then I'm saying that the total mixture, the total mass of the mixture is 100 grams. So if oxygen is 16% of it, then my mass of oxygen, you can draw a table to make your calculation easier. My mass of oxygen will be 16% times the total mass I have, and that will be 16. If let's say I chose my basis to be 1 gram, then it's going to be 16%, 16 over 100 times 1, and I'll get 0.16. Yes. So when we want to find the mass of carbon monoxide, we are choosing a basis of 100 grams, and then carbon monoxide had 4%. So just 4%, 4 over 100 times the total, which is 100 grams, and that will give you 4. So you do same for all of them to get the masses for all of them based on your basis. Then you have to note down the molecular weight of each of the gases or the component. So now you know your molecular weight of each, your masses. You can use your mass and your molecular weight to get your moles. You know moles is mass over molar mass. So 16 over 32 will give you 0.5. 4 over 28 will give you 0.14. And then you can do for all this. Now, when you get your moles, we sum them up to get your total moles, and that will be 3.279 moles. When you get your total moles, if you want the mole fraction of oxygen, then it's going to be 0.5 divided by the total, which is 3.279. When you want the mole fraction from carbon monoxide, you do the same. So you can actually use Excel to do all this. When you have your this one here, you set your, you can put in your formula and then you do your referencing or your relative references. And then you can get the moles and then your mole fraction. Okay. So when you sum up the mole fraction, you should get 1. Then realize that our mole fraction and our mass fraction were not the same. Or let's say if we want to convert them into mole percent, this would be 15%, but this one was, this would be 4.4, but this one was 4. So it means that your mass fraction and your mole fractions are not the same. Go home, you can try 50 grams. So yours will be 6 over 100 times 50. And
Yeah.
then
So yeah, that is true, but you still have to be wise. If you choose a 1 or 0, it makes the multiplication easy. So I assume, right, as compared to choosing 7. The other time you
yes,
might even have to, I don't know, round up the number. But if you choose
yes,
1, 10, 100, it makes the number. Remember, so if it's 10, then I don't know, 16% is what? Is 1.6. But
yes,
that becomes like
1.6.
straightforward as compared to you choosing, I don't know, 3. Then the numbers are all over the place.
Yes, so we will talk about this for the last time. Average molecular weight. So after getting the mixture, or let's someone might ask, what's the essence of you finding the mole fraction and the mass fraction? Sometimes you need to find the average molecular weight or the molecular weight of the mixture that we have. Eh, And then that one we find it based on our mass fraction and our mole fraction. We can use either the mole fraction or the mass fraction to calculate for our molecular weight. Now to find the molecular weight of the mixture, if you have your mole fractions, then it will be your mole fraction times the molecular weight of each of the components, and then you sum them. So for instance, if I want to find the mole fraction, sorry, the average molecular weight of this mixture, is going to be the mole fraction this of oxygen times its molecular weight 32. I'll add it to 0.044 times 28, add it to this times this, and that will give me the molecular weight of the mixture. That is when you have your mole fraction. But then if you have your mass fractions, the mass fraction is 1 over the average molecular weight is equal to the mass fraction of component A over its corresponding molecular weight. So you sum everything. The final answer you will get, you have to find the inverse of that before you can get your average molecular weight. So from this, if we wanted to find our molecular weight based on our mass fraction, it's going to be 0.16 divided by 32 plus 0.04 divided by 28 plus 0.17 divided by 44. You sum everything. When you are done, you need to find the inverse of that before you can get your average molecular weight. But then if you have your mole fraction, it just you multiply and then you sum them. And so we can try something like this. Calculate the average molecular weight of air from its approximate molecular composition of 79% nitrogen, 21% oxygen, and from its approximate composition by mass. So we are trying to compare the two and see if you're actually going to get the same answers or not. So based on the mole fraction, the mole fraction of nitrogen gas here is 0.79, and that for oxygen is 0.21. So you just have to multiply each by their molecular weight and then you sum them up. You get 29 kilogram per kilomole. And that's why you have the molecular weight of air to be around 28.9 or 29. Now using the mass fraction approach, you find the inverses. So the mass fraction divided by the molecular weight. You sum it to the mass fraction divided by the molecular weight. The answer you get, you need to find the inverse of that. Then you end up getting the same answers. So this is your assignment. I will send you the question and then you can try your hands on. You can use Excel. I think Doc also has a different assignment for you people. One more thing for gases, mole fraction or let's say mole percent is equal to a volume percent. So for this question, the volume percent here is similar to mole percent.